So everybody downloaded KiCad. I'll probably just say KiCad half the time and KiCad the other half of the time. I have no idea. So everybody downloaded that, and I think everybody downloaded also this documents from the Google Drive folder, I think. So we're all set on that. And then if you want to also open this, this other link in the browser, this other link in the browser, which is like a circuit simulator. So we'll get into all that stuff in a bit. Yeah, so just to super briefly introduce myself and Nico. We're a musical duo, and we also make our own musical instruments, and a lot of times they're electronic. And in the last 2 years, let's say, we've been pretty deep into kind of making them the way you would make them if they were a product, which kind of means collaborating with factories and what they call design for manufacturing. Basically making a design which is ready to be manufactured, which works with the machines in that kind of production so that they can be produced really easily and really reliably. And the reason that we do that, or the reason that I decided to do that, is mainly because of reliability, because we are traveling all the time. And as musicians, we wanted stuff that would not break, you know, that we could kind of rely on, but that is made just for us. So it's also about kind of creating something completely custom. And so by doing that, it's kind of opened up a lot of new possibilities for us in terms of like just being able to realize whatever we want to realize. So I don't have any background in electronics. I have a background in music. And for me, this is just another tool that I can use to create music with by creating musical instruments, basically. And so today I want to introduce a lot of different concepts, a little bit about circuit design, a little bit about different approaches to making music using circuits, but mainly on designing and creating the PCBs and that kind of collaboration that happens with the factory, let's say. Not really a collaboration, but how you prepare files for this factory so that it can come out exactly how you need it to. So does everybody know what a PCB is? Yes. I see one skeptical face. So let's say, so a PCB is, it's like that green thing in the computer that you recognize. I have one. Here. You have it? Do you put it away?
People know.
People can imagine it. And it's basically, its electrical function is basically the wires. It's all of the connections between the components. In a circuit, you have like all these components, capacitors, resistors, integrated circuits, transistors, diodes, stuff like that. And they're all connected by wires. And those wires are on the PCB, and those components are on the PCB connected by the wires. Yeah. And I first want to introduce how the PCB is made in the factory because it's fascinating. Like, it's absolutely incredible. If you send a design to the factory that this videos came from, and it is less than 100 by 100 millimeters, so it's like this much, it costs €2 to make 5 of them. So somebody, after I showed this to you, somebody explained to me why this costs like less than a sandwich, because it makes no sense. It makes absolutely no sense. But so it's basically a photographic process in that you are sort of exposing different materials and then removing them through photo processes. So that's the main thing. It's like imaging. And so the base material is called FR4, which is a kind of fiberglass. So if you look at the PCB, it really, can you get one of the, here's one we can kind of see. If you look at the side of the PCB, and it's kind of yellowy, that's the FR4. So the FR4 is kind of this beige color. And then on the outside of the FR4 is a very thin layer of copper on one side and a very thin layer of copper on the other side. So the FR4, the actual FR4 is about 1.5 millimeters thick. And then the copper is 0.035 millimeters thick. So it's very thin, the layer of copper. Yeah. Yeah, if somebody wants to pass it around, this is one we made. So this is like exactly what you receive back if you follow this whole process. So if you want to look, you can see on the side this FR4, and then you can see just how thin the copper is. It's extremely thin. Yeah, so the first step in the process is they have these large sheets of FR4, and they drill all the holes in them. So there's a lot of holes in the PCB for where the parts connect, where there's also electrical connections. So the first step is there's this machine that picks up all of these little drill bits of different dimensions and puts all of the holes in the FR4 exactly where you tell it to in the file. So that's step one. The second step is called copper deposition. So that's when this thin layer of copper is like electroplated to the outside of the FR4. So now you have the drilled FR4 with thin layers of copper on either side. Still has the holes in it, okay? So that's the second step. Then there's the imaging of the outer layers. So this is that photo process. So there's a kind of printed transparent version of your entire circuit design on a piece of film that gets exposed onto the FR4 with the copper on it. And then some kind of acid solution removes, that's the film stripping, it removes all of the copper that you don't want there and just leaves the copper of your design. So you can see that now there's copper removed based on that photo process. So that's the third step. Then this is a electroplating process. And this is because in between, inside each of these holes that you drilled, you actually want it to be electrically conductive inside the hole so that the top layer of copper and the bottom layer of copper are electrically connected. And so in order to make those holes electrically conductive, in order to make those holes electrically conductive, they do electroplating so that all of these inside of the holes also have the electrical conductivity. So then there's this automatic optical inspection. So this woman puts the board, the full panel, into the machine, and then this computer is looking at the printed copper layers and comparing it to the design files to check if they match. And it's doing that automatically based on the design files. Then the next step is called solder mask. And so the solder mask is a kind of material that you put on top of the entire circuit board, except for where you want to solder the components down. And so the solder mask, it doesn't take to the solder. The solder is not going to stick to the solder mask. And so that helps it so that when you're soldering the board, when you're connecting all the components stay where they're supposed to. They get connected where they're supposed to, and they don't get connected where they're not supposed to. So that's what makes it green. It's the solder mask. And so after that, there's the silk screen layer. And so that's all of this white markings. That has no electrical purpose. It's just there to tell you something about the PCB. So like we put these designators on the PCB. Every component has its own designator. So like resistors have the designator R. So the first resistor is called R1, and then the next one is R2. Same with capacitors, C1, C2. And so you mark those on the board so that when you are trying to troubleshoot, when you're trying to discover something about the electrical functionality of this board, you can reference the schematic and see R1, and it will match with the R1 there. So that's the printing of the silk screen. So then this is hot air solder leveling, which is sometimes called hosel. And it's a finish that covers all of these pads so that they are kind of solderable. And there are different kinds of finishes. Another one is like gold. So sometimes you see them having the gold finish, the plating of the through holes and everything. So that's this process. Yeah. And then the final step for the PCB is this flying probe test, which is basically a robot with two little needles that kind of work like a multimeter, and they're checking the continuity between every point on the PCB. And the computer is loaded with a file that says how all of the points are supposed to be connected. And so the probe just super quickly goes through every combination of those and checks that they're electrically connected the way they're supposed to be. Crazy.
I didn't
Yeah.
know that stuff.
Yeah. Okay. And so then finally they cut out the boards as they're supposed to, or there's this thing called panelization where you kind of have like multiple boards connected, but that's the last step there. Okay, and so that's the whole process for creating the PCB, but then the factory can also put all the components on and solder them too, okay? And so the way it does that, the first step is, which I didn't show here, is to create a stencil. And the stencil is a thin piece of maybe aluminum or something like that, a thin piece of metal, which has holes cut out for all of the solderable pads. And so it perfectly matches the PCB. And so you can see here the stencil will be placed. That's the stencil. And it perfectly matches all the solderable points on the PCB. And then this machine, just like you would do a silk screen on a t-shirt or something, it's spreading out this solder paste. And so the solder paste is a mix of like solder dust and flux that when heated will solder just like regular solder. And so it's perfectly placed in the right amount on all of the pads. So the PCB is like ready to take the components now. And so the next step is to use this thing called a pick and place machine. And so the pick and place machine has reels of components. So each of these things is a reel, a tape reel, just like in a tape player or something like that. And it has a specific component on it. So like this component is like one IC, and this one is like some resistor or something like that. And this arm, whatever you call that thing, has a bunch of vacuum-powered actuator things that can move over to the start of this reel, pick up a component using the air suction or whatever, and then it moves the component over here where there is a camera facing up. And the camera looks at the positioning of the part on the suction and sees how far off it is from like the origin that it's supposed to be on, and compensates where it's supposed to move exactly over the PCB. And then it places the component in the exact right orientation in the exact right spot on the PCB based on whatever difference the camera shows. And it does this insanely fast and with like 6 components at the same time. It's crazy. So it's placing all the components exactly where they're supposed to.
That's actual speed.
That's the actual speed of it. Yeah. Yeah, and so you'll see, like, when I said design for manufacturing, it's like working within the constraints of all of these machines. So there's a specific number of reels on this machine. And so if the number of components you use is the same as the number of reels, you can save money. Because instead of having a person reload the reels, they just set the reels once and you're ready to go. So that's an example of like design for manufacturing. Yeah, and there's all sorts of things you can think about with this. Like when those arms come down, it can like bend the board slightly, which can affect parts placement and stuff. So if you have a board that's like larger, it might dip in the center. There's a lot of things you can think about there. And so the last thing is this has to basically go through an oven. It's called a reflow oven. And in the reflow oven, it's kind of like a kiln for ceramics or something like that. It has a specific temperature curve that's kind of calibrated to the specific type of solder and flux so that everything kind of melts correctly and all of the components are then soldered, permanently soldered to the board. And that's kind of the last step. Yeah, so that's how the PCB is made. So what we're focusing on today is how to prepare files so that you can send your files to a factory like this and just receive a device back in the mail. Yeah. Yeah, you don't even have to solder it. It's crazy. Yeah. And yeah, you might be thinking like, how do they do the through-hole components? So they also have machines that do the through-hole components. There's like a couple different ways to do it. I think they're still manually placed in, and they kind of have this river of molten solder with little bumps in it. And the board kind of passes under those bumps in the river, and it just touches the bottom of all of the through-hole components and solders them in place. Yeah, so that's just like, that's to understand what we're designing for. Yeah, and so yeah, today what I want to do is I've kind of created this little semi-basic schematic. It's a kind of synthesizer, a little unconventional odd synthesizer, and we can all together create a PCB for it, which is ready to be sent for this kind of manufacturing process. So I do want to start a little bit to discuss what's going on in here in terms of the circuit. And then after that, we can talk about how you would put the circuit into the schematic in the software. And then we can talk about how to do the PCB. And then everybody can try on their own routing the PCB, and we can see what different solutions people come to. Okay, so I think I start with this because it's like very high level. So this is another software. We're not going to worry too much about this. This is a music production software, and it's kind of a software emulation of hardware synthesizers. And it's also open source, so people can develop their own kind of plugins for it, let's say. And I like to use it as a prototyping tool mainly, because if I want to make a musical instrument, usually all of the component parts of that musical instrument are kind of already made here. Yeah, and so it's really easy to demonstrate. And actually somebody made these plugins which are sort of software implementations of integrated circuits. And so in that sense, it's really easy to prototype an idea if it's using those integrated circuits. And this little synthesizer is all based around CMOS logic. We're going to talk about all of that in a second. But it's sort of, all of these wires will eventually be connections on the PCB. And all of the like kind of internal workings of these are going to become circuits. But this is sort of a high level version of it. So let me see if it's playing. So to play this instrument, we have this patch panel, which on our PCB is going to become switches. And based on how we switch these switches, we're going to hear different musical patterns. And we can change the pitch and the frequency that the rhythm is happening at. Yeah, so we're going to try to create this as hardware, starting from this software level thing. But we don't have to dive too much into how this software works or anything like that, just that basic explanation that we're making a circuit that does the same thing that this software is emulating. And this is kind of a programmable synthesizer, because if you had two of these units in front of you, if one person pushes their switches in this configuration, they're going to hear the exact same sound as you. So it's programmable in that sense. Yeah, so let's look at the circuit for this. Okay, so this is the circuit to emulate, or to actually physically create the same thing using circuitry. And it's all based around CMOS logic integrated circuits. And so, well, does everybody know what an integrated circuit is? Okay, we're gonna say yes?
No,
No.
Yeah, explain it if you
Yeah,
can.
so if you have a circuit is a bunch of components working together. An integrated circuit is like that entire circuit squished down into a little chip with pins on it. And the pins have different functions depending on what the circuit is in the integrated circuit. So if it's, so this is a schematic. It's like an abstraction of the integrated circuit. And these are all of the pins with their different functions. So this one is power. So you connect it to power. That's like its function. And this one is ground, and you connect it to ground, and that's its function. So they have different functions. But this completely depends on how the chip was manufactured. They all do different things. They all have different numbers of pins. Yeah. So
did you design these yourself from scratch, or did you export it from that software?
Oh, no, you can't do that. You can't do that. If only. If only. Yeah. I don't think you could really create that software because, there's so many different ways of implementing the same result. If you just want an oscillator, if you just have like a square wave oscillator, there's like 100 different circuits that could make a square wave oscillator. And they'd all be like a little bit different, and you have to decide which one you want to use and why, But I think, so if we can go into this, this Fallstat now that I think everybody has open. And we can start breaking down, this circuit. So, let's go. I'm going to try to not spend super much time explaining all of this stuff because it can just become an all-day activity if you just keep asking why. And at a certain point, I also just don't know, I don't remember who said this. Maybe this is a common thing. But some people are like, there's just magic elves inside of the components, and that's the reason that they operate the way they do. And at a certain point, it's quite beneficial to just go with this magic elves thing at a certain level of understanding. So, yeah. Anyway, so this circuit, super simple circuit, it has a resistor and a capacitor, and it's a filter. It's a low-pass filter. And it has a name. It's called an RC filter because it has a resistor and a capacitor in it. And so if we want to learn how to use this simulation software quick, if you press R, you can make a resistor. If you press C, you can make a capacitor. If you press G, you can make ground. If you press W, you can make wires. And if you press Shift V, you can make a voltage source. So you can do that very quickly. The hotkeys are very easy to remember. They're just the letter of the thing you want. Just remember Shift V for the voltage source. And if you double click the voltage source, you can change what type of voltage source it is. So right now it's 5 volts DC, so just like a steady 5 volts. But I'm going to turn it into a square wave. So right now it's basically an oscillator. And its max voltage is 5 volts. But there's no DC offset. That means it's oscillating with plus 5 volts and negative 5 volts at a frequency of 40 hertz. So 40 times a second, it's going between plus 5 volts and minus 5 volts. So we can probe any part of this circuit and look at it in a scope. So if we look at this view in new scope, we can see, it's very faint here, but you can see it oscillating. Here's the square wave. And if we view this in the same scope, you can see the result of the output. Just to try to explain this quickly. So a capacitor, it's like a little battery, okay? So it's gonna store some charge and then it can be discharged. And a resistor is like resisting the amount of current. So when you have the resistor next to the capacitor, the rate at which the capacitor charges and discharges is going to become slower because instead of immediately charging, there's this resistance that slows down the speed at which the capacitor can charge and discharge. So why is this filtering high frequencies though? It's filtering high frequencies because it's slowing down the speed at which the square wave can shoot to the positive voltage. It's taking this super fast rising edge and it's slowing it down because the capacitor needs to charge. And then when the capacitor is discharging, similarly, it's slowing down the falling edge of the square wave. So there's a lot of different ways of conceptualizing the frequency spectrum present here. But if you think about the rising edge, how fast that is, that's how much high frequency content is present. So a sine wave, we all know what a sine wave looks like. That is kind of the slowest possible rising edge. The triangle wave, it's somewhere in between. This is somewhere in between. So the amount of high frequency content present is related to how quick that rise and fall time is. So triangle waves have less high frequency content than square waves, and sine waves have even less high frequency content than triangle waves. And so square waves have, is everybody generally following that? And there's also a reduction in amplitude, right? Because and if we add more filtering, eventually we're going to have no.
Can I ask something? Is that the actual reason why we have these filters is, I don't know, when we have an instrument is producing some signal, let's say it was producing the square signal. How would that sound in comparison? So we can understand.
Definitely. Okay, so well, I'll just say one other quick thing and then we come back to this. So you can also discuss these filters in terms of how much of a reduction there is in decibels per octave. So this RC filter, you would say it has -3 dB per octave. So it means if you double the frequency, that's an octave, by the way, so an octave is doubling the frequency. So if this is 40 hertz, right, it means that at 80 hertz, it'll be 3 dB quieter. Yeah, and at 160 hertz, it'll be -6 dB quieter, okay? So that's a -3 dB per octave. And so if you chain these together, you now have a -6 dB per octave filter. So these are called poles of the filter. So right now you have a 2-pole low-pass filter with -6 dB per octave. And so if you look at the signal here, oh, that's not the one filtering. Yeah, sorry. I'll change this to be square again. So if you look at the signal here, you can see the sharper cutoff makes it more sinusoidal. Because the cutoff, where the frequencies are being cut off, is happening more dramatically. And so you're closer to the fundamental frequency of the wave, which is the sine wave. So if you add 4 poles, this will really look like a sine wave. If you have 1 pole, it'll really look like a triangle wave. Yeah, and by the way, the harmonics of the square wave and the triangle wave, they're the same. The only difference is the rate at which they decrease in volume. On the square wave, it has a specific curve that it reduces volume over the harmonics. And at a triangle, it's a different curve and it's much more dramatic. So on the triangle wave, the harmonics get quieter much faster. So that's why this looks triangular when you start reducing those frequencies. And anyway, to just listen to how it sounds, so the reason I introduced the concept of poles is because this circuit, pseudo circuit, emulated circuit, is a -24 dB low pass filter, I think. I mean, that's like the most common one in music production, which means 4 poles. So -12 dB is 2 poles. And that's because we were talking about -3 dB. It doesn't matter. They're different filters. They have different slopes. So this one has -4 dB per octave. So if we put the square wave into the low pass filter and we just listen, so. Okay, so that sounds like a square wave. As you cut off frequencies, it sounds softer. Well, there's some
So
clipping
with
there.
that, with the knob at the top, what are you changing? The amplitude of the frequency?
You're changing the cutoff frequency of the filter. So what you're essentially doing, if you want to translate it into this circuit, what you're essentially doing is dimensioning this resistor. You're changing this resistor's value because this, remember we said this resistor is changing the speed at which this capacitor can charge and discharge. So if it, yeah, that's what I'm doing. So look at this red, that's the filtered one. Or I think, this is getting confusing. So this red is the filtered one. So if I change this resistor to be bigger, it's going to become, see how much quieter it got? Because it's filtering more frequencies there. And then if I make it really small, it's just like it's not gonna filter anything. The red is now the square, you know? And if you do like 500 ohms, it's something in between. So you're just taking this rising edge and slowing it down. That's it. So if, you know, a variable resistor is a potentiometer. So if you replaced this with a potentiometer, you would be kind of emulating what is happening in that software. If you want to get picky into the specifics, there's a lot of differences. There's the slope of the cutoff and a lot of other functionality here, but it's essentially the same.
So this is just a low pass filter.
It's just a low pass filter.
How would a high pass filter? Like
Let's talk about it.
Just the reverse? Oh, you mean
It's very simple. I was going to talk about it at the much later because it comes up later in the circuit, but let's talk about it. It's super easy to talk about. It's super easy to talk about. So all you have to do is switch the capacitor and the resistor. And so if you look at it, it kind of makes sense. The capacitor charges immediately when this wave goes through, and then when it goes to discharge, it does so slowly. So I kind of want to increase this so that it becomes really clear here. No, I want to reduce it. Wait a second. Let me mess with these until I get a result that makes this really understandable. There you go. So if you look at the red one, here, you have this sharp beginning of the square wave, and then it immediately drains out. And so you can kind of imagine why this means there's a lot of high frequency content present. Because I said the rising edge is where the high frequency content is. So the rising edge is retained, okay? And so the reason I was gonna talk about this later and the reason it comes up in the circuit is something that might sound a little abstract now, but it will come into play in the circuit, which is called AC coupling. So this might come up in music production actually sometimes. So you have DC coupled circuits and you have AC coupled circuits. And audio circuits, they tend to be AC coupled. And that means that the voltage, the signal, the analog signal of the audio is rotating around 0 volts. It's not rotating around 5 volts, you know? And so when you put in this high pass filter, no matter what DC offset there is here, so if I add 5 volts of DC offset here, it's still going to rotate around 0 volts at the output. I know it's a little bit hard to see there, but you can see.
If you hover it, it becomes
okay. The green one, the square wave, this original square wave, is now, it's only going to 0 volts. It's not going down to -5 anymore. But still the output is rotating around 0 volts. And so the reason for this is because, so a high pass filter, it lets high frequencies pass. It filters out low frequencies. DC voltage, a steady voltage, is essentially 0 hertz. It's essentially a signal with no frequency because it's never moving. So a 0 hertz signal is always going to be filtered by a high pass filter. If there's any cutoff frequency, it has to be above 0 hertz, okay? So by putting in the high pass filter, you're removing DC offset, but you're also removing some low frequency content. If you make this capacitor larger, you reduce the amount of low frequencies you remove, but see, this is more square-like, but it still floats down to rotating around 0 volts. Okay, and so that is used in the circuit because in the final output, all of our signals in the circuit are not rotating around 0 volts, but then when we have the final output, we want them to, so we use this circuit. And normally when you see this circuit in the wild, you don't see this resistor, you just see the capacitor. And that's because this resistor is present either literally or abstractly, let's say, in the following circuit that it's connected to. Because every circuit can be conceptualized as a load, as a resistance. And so there is going to be some resistance to ground between this capacitor. So it will always serve this AC coupling function. So that resistance could be just your headphones. It's still going to serve the same purpose. As long as this capacitor is big enough, this resistor can basically be any value. You know, I mean, it's not going to be terribly large in general. Yeah, so that's the high pass filter and the low pass filter. So
Can you change the scope and turn it into a frequency scope?
let me, yeah, let me, I've never tried that because this is in real time and it would need to like do the analysis. And when we take a break, I'll figure it out and show you. Yeah. I don't know if it can do that. Yeah. So we're going back to the circuit. So we didn't cover that much of this, but we'll get there. Yeah. So this is the AC coupling at the end. So that's for the AC coupling part. And this resistor is here as a kind of short circuit protection. It's there so that if you connect this somewhere it's not supposed to be connected, it can't create a short circuit because there's some resistance there. So that's the final output of the synthesizer. So we're going to focus in now on this circuit here. Okay. So the next building block we need is a Schmidt trigger. Wait a second, that's not the right one. We want an inverting Schmidt trigger, excuse me. Okay, so to find that, you go to active, you right click, you go to active building blocks, and you go to add Schmidt trigger inverting. Who here knows what a Schmidt trigger is already? Oh yeah. Makes a great password. No, I don't know.
Who was Schmidt?
The guy who invented the Schmidt trigger. Yeah. I don't know. Maybe not. Okay, so Schmidt trigger is so yeah, another thing I want to talk about is the difference between analog and digital circuits, because I think this specific circuit lies in this very interesting space in between digital and analog. And maybe we can have a discussion about whether we think it's analog or digital. But so does everybody know that there's analog computers in existence? Mm-hmm. Yeah. So what is an example of an analog computer?
Well, like the original Mac?
No, that's a digital computer.
Oh, it's digital?
Yeah, definitely.
It needs to have something moving literally, I guess.
Well, not necessarily. There are electrical analog computers also. Yeah. So I think the best example of an analog computer is the steering wheel in a car, because you rotate the steering wheel and it computes the way that the wheels are supposed to move. But they're not exactly related. There's a mechanism there that translates your input into the computer, where the steering wheel is, to where the wheels are supposed to go in the car. That's an analog computer. There are also electrical analog computers. There's a lot of overlap between analog synthesizers and analog computing. Like a low-pass filter made in a different way than this RC filter is also an integrator. It can also be used for integration, like calculus integration. They're kind of the same thing. So there's a lot of overlap between analog computing and analog, like electronics and synthesis. But anyway, the main thing I would say about analog circuitry is that the signal is the actual thing you're listening to. It is not a conveyor of some information that gets encoded and decoded. It is the information. You are listening to the actual circuit to get the information. When you create a sine wave, you are listening to the sine wave. You're not encoding it into bits and then decoding it back out. It doesn't matter how it sounds, like they may sound the same, but for me, that's the difference, is this translation. And so this Schmidt trigger is actually a big part of what makes digital very important in the modern world, because the main thing that makes digital so much more reliable than analog is the fact that the signal is not what you are listening for. You have a chance to recover a noisy signal many, many times when you do a digital circuit, because every time the signal goes to a new circuit, a new IC, as long as the output can tell whether the input was high or low, it's good enough. When you have an analog signal, all the noisiness that's in that signal is there because you're listening for it. When you have digital, you just have to tell the difference between 0 and 1, that's it. And so the Schmidt trigger's main use is for helping us tell the difference between 0 and 1, recovering these noisy signals. And so the first step to understanding this is just understanding the inverting part, which is super easy to understand. So at the input, you're always going to have the opposite at the output. So right now the input is 0 and the output is 1. But if I put a 1 at the input, the output becomes a 0. It's just like that. And then to understand the Schmidt trigger part, I'm going to edit this with this sliders function to be able to change the voltage. And then it's going between 0 and 5. So now I can control the voltage here. So if it's at 5 volts, if I have a noisy signal, see it's moving up and down, the output is still 0, it doesn't care. But then if it goes low, it goes lower and lower and lower and lower and lower. Eventually it's gonna pass a threshold and bang, it's now a 1, okay? And then if I have this noisy signal at the low one, okay, it's kind of 0, it's kind of 1, whatever, it doesn't matter, as long as it doesn't pass this higher threshold. So now we're gonna pass that higher threshold and bang, it's a 0 again, okay? So it has these two thresholds, and as long as it doesn't cross that threshold, the output stays what it's supposed to be. So those thresholds is what makes it a Schmidt trigger. So how can we turn this Schmidt trigger into an oscillator? We can turn it into an oscillator by using feedback. Because imagine, if you take this 1 at the output and you put it into the input, what is it going to tell the Schmidt trigger to do? It's going to tell it to output a 0. And then as soon as it outputs a 0, it's going to have to output 1. Okay, so that is creating an oscillator. It's creating oscillation. But the oscillation is very fast and very unreliable. And the only thing that's stopping this is like the propagation delay of the circuit. It's just instantly trying to do this operation. But we already have learned about a circuit that can slow this down. So what is the circuit that can slow this down? The low pass filter, exactly. So we're gonna put our low pass filter. So the output here, it's coming here, it goes through the resistor, it goes through the capacitor to ground, and now we have this nice stable square wave oscillation at the output. And if we look at the input, we have the filtered version of the square wave oscillating between the two thresholds of the Schmidt trigger. So this is the positive going threshold, that 3.3 volts, and like the 1.75 volts is the negative going threshold for the Schmidt trigger. So we have this triangle-ish thing filtered there, and then the square wave there. So that is present in the schematic. That's the exact circuit. Okay?
4106.
Yep.
Each one is an out. Each output is a Schmidt trigger.
Mm-hmm. Yeah. Yeah. So if you want to change the frequency of this, you just have to change the cutoff frequency of the filter. Because if you slow down this rising edge more, the amount of time it will take for the Schmidt trigger's threshold to be reached is going to increase. So if I make this bigger, the oscillation becomes much slower, right? And then if I make this smaller, now the oscillation is much faster. Okay? So in the schematic, we've added one resistor in series with a potentiometer. So this is here so that the minimum resistance is always like 1K. And this is here to change the frequency. And so this simulator is far from perfect, but it's quite good for sort of dimensioning components like this. So you can decide what values you want these to be by putting this into the simulator and sort of messing around with these values until you're getting the frequency range you want. Yeah, so that's how this circuit was designed. And so we were talking about integrated circuits. We need to identify how in the real world from the simulator we can find this inverting Schmidt trigger. And so there are manufactured probably thousands of integrated circuits which each have Schmidt triggers. One which is really common is this 4106 chip, which contains 6 of these inside of the chip. And so these are pins 3 and 4, but if you look here, there's a bunch of unused ones. And so there's 6 of them inside of the chip. So to set up this entire schematic, all you need is you need this part, and then you need the power. So in this software, ICs, they can either be shown as one IC with all of the pins, or they can be shown in multiple sections. So this says U1G, and this says U1E, U1F. So these are all part of U1, integrated circuit 1, but they're each different sections of it. So this represents pin 9 and 8 of that integrated circuit, and this represents 5 and 6. So this one shows the power supply. And the one other component you need, which can be quite important, is this decoupling capacitor, bypass capacitor. And this is for filtering the power supply when it goes to the chip. This is kind of something you can pretty much do on every IC you ever use. And this needs to be placed right next to the chip. And the size of the capacitor depends on how high frequency noise you're filtering out from the power supply. So a larger one deals with lower frequencies and a higher one deals with higher frequencies. And you can basically think about it like this, I guess. This is like a little battery. If you unplug your device, this chip for some period of time will be powered by this capacitor. So you can think that if the power supply is not stable, this will help stabilize it before it goes to this chip. So that's quite important. But other than that, that's all you need to set up this. Okay, so if we keep going like this, I don't know if I have to speed up so we can get to the KiCad stuff, but maybe the rest of this stuff doesn't need to be simulated too much. We can just look directly at it. So this next integrated circuit is a binary counter. And so a binary counter, it counts in binary. So it takes this clock input, which is our oscillator, and it outputs counts in binary on these outputs. And it has 12 bits, so it has 12 outputs. And when you count in binary, you're basically dividing the output. So this output is going to be half the frequency of this input. This one is going to be half the frequency of this. This is going to be half the frequency of this. And this is going to be half the frequency of this, just like that. So you can also simulate that here pretty easily. If you go to digital chips, add counter. This is 4 bits. If you put it here, you can see, let's slow this down a bit. You can see bit 0 is flashing pretty quickly. This one is half the speed. That one's half the speed as that. They get slower and slower. Okay, so that's the binary counter. So musically speaking, so binary counter obviously very useful in computing and digital stuff. In terms of music, a binary counter is an octave divider. So you're going to get a sub-octave of your original pitch. You're going to get 4 octaves, up to 4 octaves below from this binary counter. So this oscillator in our circuit is kind of the rhythm oscillator, which is why it has such a big capacitor, because we're doing slow stuff. It's not really audio rate stuff. It's there for the rhythm. And we can choose 4 different speeds because we have 4 different bits for these binary counters. And those 4 different speeds are going into our little interface, our patching matrix. And they're going through these diodes to all the switches. So a diode is it's like a one-way street. Electricity is only going to go in the direction of this arrow. It's not going to go this way. So that's so all the outputs don't short together. And so this is like a little patching matrix. So all of the highest octave rhythm goes here, 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 and here. And then where can they be routed to? They can be routed as the selection bits for this whole part of the circuit. And so this whole part of the circuit, there's 2 of them identical. Gonna try and go a bit faster here. So here we have a different type of counter. We're gonna talk about it in a second. Now here we have a multiplexer. So who knows what a multiplexer is already? Okay. So multiplexer is like selecting between all of these inputs. So you have 8 inputs here, and you can route any one of those 8 inputs to the output. If I want to route input 1, input 0, let's say, to the output, then what I need to do is send to the chip from these A, B, and C a binary 0. So binary 0 is 0, 0, 0. So if I connect these all to ground, then this output is just going to be a copy of this input. Now, if I flip A to 1, then I'm going to be selecting the second one because I'm just giving it the binary number. If I put these 2 both up, then we have 3. And so that's going to select this one, put it at the output. Okay? Yeah. Yeah. So yeah, and so this is something you can use. I mean, the way these are used, it's more like, so you have a microcontroller with a limited number of inputs, but you want, let's say you have like 4 potentiometers here, and you want to send them all to 1 pin on your microcontroller. You can use some code to scan through all of these inputs really quickly and sort of effectively have all of the information at the same time. That's how it's normally used. But in this case, we're just kind of using it to very slowly select between these outputs. So what are these outputs? These are the outputs of a different type of counter. It's not a binary counter, but it's a decade counter. So instead of counting in binary, it just counts the way humans do. It just goes 1, 2, 3, 4, 5, 6, etc. So this one is high, then this one is high and the rest are low, then this one is high, then the rest are low, every time it gets the clock signal. And so we're not, usually you see this used for timing something or for sequencing or something like that, but in this case we're using it for pitch, okay? So we are clocking this very quickly. So if octaves are dividing by 2, like the binary counter, what is this division going to be? This division is going to be subharmonics. A little bit hard to conceptualize if you're not like into music and stuff. For the more music-oriented people, so this is like subharmonics written in musical notation. So the first division, if you divide by 2, then you're in the same world, you get an octave. If you divide by 3, you get an octave and a fifth. If you divide by 4, you get 2 octaves, and so on. Dividing by 5, you get this major third difference, perfect fifth difference, etc. So those are the tones that are generated by this. And that's why when you heard the original patch, when you hear the original patch, you hear these musical tones because they're those subharmonics. And by sending different binary numbers to the multiplexers, we're choosing which of those subharmonics are getting played. So the multiplexer's output, it gets routed to the reset of the timer, because if we want to divide by 6, then we want to reset it at 6, so that's the periodicity of the oscillation. If we want to divide it by 2, we want to reset it at 2, so that's the periodicity of the oscillation that's coming out of here. And so we have 2 of these identical circuits, and then they both go through these 2 diodes together, and that is kind of like a mixer. In this case, it's an OR gate. It's saying either of these 2 outputs gets put to the headphones. That's it. So that's the whole circuit. So you have the oscillator that's timing the fast subharmonic generator going to the multiplexer thing. You have the rhythm oscillator that's timing this binary counter. And then you have your interface, which comes in the form of the 2 potentiometers to change the frequency, and all of the switches to decide which of those bits are going where. Okay, so that's an introduction to the circuit. And so now we're going to talk about how you actually make this. So now we're actually in KiCad world, but yeah, I didn't want to do something like I want, we can learn something, yeah. So in KiCad, basically the first step is putting your schematic in here. So if everybody opens the one that says download.
Sorry, what's the AC that you're covering right now? No.
This one.
I think you called it the timer, not the multiplexer, the other one.
This one.
Yeah, what's it called?
It's called well, this one is a 4017 chip.
Not a specific one.
It can be called either a ring counter or a Johnson counter or a decade counter. Sometimes it's referred to in different ways. Decade because it's for like counting tens. I don't know why the other names are, but yeah. So 4017, and then this one is 4051 is the multiplexer. These are all super common versions of these.
Can we find them in the simulator?
Yes. So if you find them in the simulator, so you go back to digital chips. If you add a multiplexer, so in the simulator, everything's really generic.
Yeah.
So here you have 2 selection bits, and these are your inputs and your outputs. Yeah. And then for the ring, it's called a ring counter here. So there's your, and they did it with 10. That's like the classic thing. And this is the reset and the chip enable. So sometimes you see this line here. That means that the input is inverted to what you expect it to be. So it's like active when it's low and inactive when it's high. Sometimes you can also see that as a circle. I don't know if that's, yeah. So chip enable, it's an active low. I have it low because I want the chip to be enabled. If you put it high, it's going to disable the chip. And see, this one's inhibit, whatever. You get the point. So yeah, and then this little triangle is usually for the clock input. Yeah, and see circle because this is inverted, so circle on the output. Yeah, and this can all run on 5 volts, so I just have it going from this USB as the power.
Can I ask something about your choice of chips?
Yes.
From what I get when you do digital logic with big ICs, like through whole components for hobby stuff, you either get the 4000 series that you use here, or the 7400.
Yep.
Which one should we pick? What's the big difference between them? And which one is more available today?
I think which one is more available today is a month-to-month question, because it's kind of hard to find everything. So you can just search. They're both very widely available. I think So I think, I forget if they have the same operating voltages. I want to say that the CD 4000 ones have the higher operating voltage and the 74HC ones only go up to 5 volts.
From what I remember, they're both from the same family, so they can be both used from 0 to 5 volts situations, and they can be interchanged, but isn't the 4000 series discontinued, or is it still in active production?
It's definitely still in active production.
Very, very much.
Yeah, but I think, so 74HC is like updated. I'm pretty sure they switch faster, like the rise and fall times are faster and stuff. You just have to like go through the data sheet and find detail to find the differences. I think, you know, generally in these situations, like most of the time it's not gonna make a difference. I think, yeah, most of the time it's not gonna make a difference.
So basically whatever ties up with whatever has in their stocks right now.
Yeah, I recently thought, I was recently working on something with a 4013. So that's the D flip-flop one. And it didn't switch. And I needed to add a capacitor to slow down the rise and fall times on the chip, because the more modern one was switching too fast for compatibility of what was going into it. So, I mean, sometimes you got to read the fine print, but it's like, it really depends on what the requirements of the circuit are. Most of the time, it doesn't matter so much.
The 7,000, the one you said, 74,000. I think they're a lot more sensitive. I think. I don't know if that's true.
Sensitive to
As in like
touch
can
or
get damaged, yeah, like that kind of stuff. These ones you can just yeah. I think I don't know if that's true though.
Yeah, I don't know. Yeah, but